Message-Passing Dataflow. We have been looking at the different ways encoded data flows from one process to another. So far, we've discussed REST and RPC, where one process sends a request over the network to another process and expects a response as quickly as possible, and databases, where one process writes encoded data and another process reads it again sometime in the future. In this final section, we will briefly look at asynchronous message-passing systems, which are somewhere between RPC and databases. They are similar to RPC in that a client's request, usually called a message, is delivered to another process with low latency. They are similar to databases in that the message is not sent via a direct network connection, but goes via an intermediary called a message broker, also called a message queue or message-oriented middleware, which stores the message temporarily. Using a message broker has several advantages compared to direct RPC. It can act as a buffer if the recipient is unavailable or overloaded, and thus improve system reliability. It can automatically redeliver messages to a process that has crashed, and thus prevent messages from being lost. It avoids the sender needing to know the IP address and port number of the recipient, which is particularly useful in a cloud deployment, where virtual machines often come and go. It allows one message to be sent to several recipients. It logically decouples the sender from the recipient. The sender just publishes messages and doesn't care who consumes them. However, a difference compared to RPC is that message-passing communication is usually one way. A sender normally doesn't expect to receive a reply to its messages. It is possible for a process to send a response, but this would usually be done on a separate channel. This communication pattern is asynchronous. The sender doesn't wait for the message to be delivered, but simply sends it and then forgets about it. In the past, the landscape of message brokers was dominated by commercial enterprise software from companies such as TIBCO, IBM WebSphere, and Web Methods. More recently, open-source implementations such as RabbitMQ, ActiveMQ, HornetQ, NATS, and Apache Kafka have become popular. We will compare them in more detail in Chapter 11. The detailed delivery semantics vary by implementation and configuration, but in general, message brokers are used as follows. One process sends a message to a named queue or topic, and the broker ensures that the message is delivered to one or more consumers or subscribers to that queue or topic. There can be many producers and many consumers on the same topic. A topic provides only one-way data flow. However, a consumer may itself publish messages to another topic, so you can chain them together, as we shall see in Chapter 11, or to a reply queue that is consumed by the sender of the original message, allowing a request/response data flow, similar to RPC. Message brokers typically don't enforce any particular data model. A message is just a sequence of bytes with some metadata, so you can use any encoding format. If the encoding is backward and forward compatible, you have the greatest flexibility to change publishers and consumers independently and deploy them in any order. If a consumer republishes messages to another topic, you may need to be careful to preserve unknown fields to prevent the issue described previously in the context of databases. Figure 4-7. The actor model is a programming model for concurrency in a single process. Rather than dealing directly with threads and the associated problems of race conditions, locking, and deadlock, logic is encapsulated in actors. Each actor typically represents one client or entity. It may have some local state which is not shared with any other actor, and it communicates with other actors by sending and receiving asynchronous messages. Message delivery is not guaranteed. In certain error scenarios, messages will be lost. Since each actor processes only one message at a time, it doesn't need to worry about threads, and each actor can be scheduled independently by the framework. In distributed actor frameworks, this programming model is used to scale an application across multiple nodes. The same message-passing mechanism is used, no matter whether the sender and recipient are on the same node or different nodes. If they are on different nodes, the message is transparently encoded into a byte sequence, sent over the network, and decoded on the other side. Location transparency works better in the actor model than in RPC, because the actor model already assumes that messages may be lost, even within a single process. Although latency over the network is likely higher than within the same process, there is less of a fundamental mismatch between local and remote communication when using the actor model. A distributed actor framework essentially integrates a message broker and the actor programming model into a single framework. However, if you want to perform rolling upgrades of your actor-based application, you still have to worry about forward and backward compatibility, as messages may be sent from a node running the new version to a node running the old version, and vice versa. 3 popular distributed actor frameworks handle message encoding as follows. akka uses Java's built-in serialization by default, which does not provide forward or backward compatibility. However, you can replace it with something like protocol buffers, and thus gain the ability to do rolling upgrades. Orleans by default uses a custom data encoding format that does not support rolling upgrade deployments. To deploy a new version of your application, you need to set up a new cluster, move traffic from the old cluster to the new one, and shut down the old one. Like with akka, custom serialization plugins can be used. In Erlang OTP, it is surprisingly hard to make changes to record schemas despite the system having many features designed for high availability. Rolling upgrades are possible, but need to be planned carefully. An experimental new maps data type, a JSON-like structure, introduced in Erlang R17 in 2014 may make this easier in the future. Summary. In this chapter we looked at several ways of turning data structures into bytes on the network or bytes on disk. We saw how the details of these encodings affect not only their efficiency, but more importantly also the architecture of applications and your options for deploying them. In particular, May services need to support rolling upgrades, where a new version of a service is gradually deployed to a few nodes at a time, rather than deploying to all nodes simultaneously. Rolling upgrades allow new versions of a service to be released without downtime, thus encouraging frequent small releases over rare big releases, and make deployments less risky, allowing faulty releases to be detected and rolled back before they affect a large number of users. These properties are hugely beneficial for evolvability, the ease of making changes to an application. During rolling upgrades, or for various other reasons, we must assume that different nodes are running the different versions of our application's code. Thus, it is important that all data flowing around the system is encoded in a way that provides backward compatibility. New code can read old data, and forward compatibility. Old code can read new data. We discussed several data encoding formats and their compatibility properties. Programming language-specific encodings are restricted to a single programming language and often fail to provide forward and backward compatibility. Textual formats like JSON, XML, and CSV are widespread, and their compatibility depends on how you use them. They have optional schema languages, which are sometimes helpful and sometimes a hindrance. These formats are somewhat vague about data types, so you have to be careful with things like numbers and binary strings. Binary schema-driven formats like thrift, protocol buffers, and Avro allow compact, efficient encoding with clearly defined forward and backward compatibility semantics. The schemas can be useful for documentation and code generation in statically typed languages. However, they have the downside that data needs to be decoded before it is human-readable. We also discussed several modes of data flow, illustrating different scenarios in which data encodings are important. Databases, where the process writing to the database encodes the data and the process reading from the database decodes it. RPC and REST APIs, where the client encodes a request, the server decodes the request and encodes a response, and the client finally decodes the response. Asynchronous message passing using message brokers or actors, where nodes communicate by sending each other messages that are encoded by the sender and decoded by the recipient. We can conclude that with a bit of care, backward/forward compatibility and rolling upgrades are quite achievable. May your application's evolution be rapid and your deployments be frequent. Java Object Serialization Specification, docs.oracle.com, 2010, Ruby 2.2.0 API Documentation, rubydoc.org, DEC 2014. The Python 3.4.3 Standard Library Reference Manual, docs.python.org, February 2015. XML is a poor copy of S expressions. C2.com Wiki. Matt Harris. Snowflake. An update and some very important information. Email to Twitter Development Talk mailing list. October 19, 2010. Judy Sandy Gal C. M. Berberg McQueen and Henry S. Thompson. XML Schema 1.1. W3C Recommendation. May 2001. Francis Gallig, Chris Sipp, and Gary Court. JSON Schema. IETF Internet Draft, February 2013. Yakov Shafranovich. RFC 4180. Common Format and MIME Type for comma-separated values CSV files, October 2005. Message Pack Specification, msgpack.org. Mark Slee, Aditya Agarwal, and Mark Kwiatkowski. Thrift, Scalable Cross-Language Services Implementation, Facebook Technical Report, April 2007. Protocol Buffers Developer Guide. Google, Inc. Developers.google.com. A matrix of the features each individual language library supports. Wiki.apache.org. Tony Hoare. Null references. The $1 Billion Mistake. At QCon London. March 2009. Gwen Shapira. The Problem of Managing Schemas. Radar.O'Reilly.com. November 4, 2014. Russell Housley, Warwick Ford, Tim Polk, and David Solo. RFC 2459. Internet X.509 Public Key Infrastructure. Certificate and CRL Profile. IETF Network Working Group. Standards Track. January 1999. Lev Walken. Question. Extensibility and dropping fields. Lionit.info. September 21, 2010. Roy Thomas Fielding. Architectural Styles and the Design of Network-Based Software Architectures. PhD Thesis. University of California, Irvine, 2000. Jim Waldo, Jeff Wyant, Ann Woolrath, and Sam Kendall. A Note on Distributed Computing. Sun Microsystems Laboratories, Inc. Technical Report TR94-29. November 1994. API Upgrades Stripe, Inc. April 2015. Philip A. Bernstein, Sergey Bykov, Alan Geller, et al., Orleans. Distributed Virtual Actors for Programmability and Scalability. Microsoft Research Technical Report MSRTR 2014-41. March 2014. Microsoft Project Orleans Documentation. Microsoft Research. .NET.GitHub.io. 2015.